forms. And so we are not going to discuss that. We're going to leave it at this. And let's now talk about the third method of heat transfer, that is the radiation. Radiation, what does that mean? Radiate. To radiate means to throw out. Now, the third method I can distribute my chocolate is I can take one chocolate and say, Thomas, catch. Is that right? I can pick another one and say, Rachel, catch. I can throw each piece of chocolate to my class. Radiation. Most all the energy that we receive from the sun is in the form of radiated energy. Sun simply throws its energy in the surrounding medium. Heat is a form of electromagnetic radiation. I want you to get an understanding of electromagnetic radiation. You see, when you heat an object, the object will give out radiation. It will throw away chunks of energy. This object at this temperature is giving out energy, chunks of energy called quantas of energy. I am radiating energy. We all radiate energy. And this radiated energy is a form of electromagnetic radiation. In fact, electromagnetic radiation comes in all different forms. Now, what are the different forms of electromagnetic radiation? Electromagnetic radiations are waves. They got wavelength and frequency. Now, the longest of the electromagnetic radiations are called radio waves. As the waves get shorter, you get microwaves, you get infrared. Infrared are heat rays. You get the visible light. You see, the light that makes us see things is a part of the electromagnetic radiation. And as the wavelengths get smaller and smaller and smaller, the energy of radiation increases. So you must have a fair understanding of electromagnetic radiation. Objects radiate energy in the form of electromagnetic waves at all temperatures, even at very low temperatures. The effects and properties of such radiation depends on the wavelength of the radiation. Right? Now, all these radiations, one characteristics of these electromagnetic radiations, all these radiations will travel in free space with the same speed. Now, what is the wave equation we discussed in Unit 1? Anybody recall the wave equation? V equal to F lambda. And for electromagnetic radiation, the speed is generally described using C. So we say C equal to F lambda. Now, for all radiation, C is a constant. C doesn't change. So if C doesn't change, when the wavelength increases, the frequency has to decrease. When the wavelength decreases, the frequency has to decrease. Now, heat waves are called infrared radiations, and they consist of larger waves than visible light. All right. Now, let me see if I can illustrate that by drawing waves for you. Now, the longest of all waves, if this is a very long wave, well, that could be a radio wave. Now, if the wave now becomes smaller, it could be a microwave. Now, it becomes smaller, there you have infrared. Infrared. And here you have visible light. Now, don't confuse here. When I draw these diagrams, don't think that all radio waves, you have only one type of radio waves. there are hundreds of thousands of different radio waves of long and short. We group them all together and call them radio waves. In the same way, visible light. Visible light consists of about 4,000 different waves. And you know, each wave is a color. So visible light actually contains about 4,000 different colors. I simply represent it by this wave, but it's a combination of 4,000 different waves. And as you go shorter and shorter, you get ultraviolet, X-rays, gamma rays, and so on. So electromagnetic radiations come in all different flavors of wavelength and frequency, but they all travel with the same speed. Now here I have a picture of the electromagnetic spectrum. There is the wavelength, look at that, wavelength in kilometers down to micrometer, 10 to the negative 6 meter, to nanometer, to picometer. You can see wavelength decreases. Now you can see here, what are the types of waves here? Radio waves, very long wave. Radio waves can be kilometers long. And you can see all these waves are classified radio waves, almost up to here. And now comes the microwaves. Wavelength about 10 to the negative 2 to about 10 to the negative 4. They are microwaves. Then these are the heat rays. You see, light alone does not carry heat. Heat rays are different radiations. So these are heat rays about 10 to the power of negative 4 to 10 to the power of negative 6 meter wavelength. They are very small waves. And look at the visible light. Visible light is only a very small part of the electromagnetic spectrum. And as the wavelength increases, you see that 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, and nanometer, you got X-rays. So, electromagnetic radiations come like radio waves, microwaves, heat radiations. Now, the radiations that we give out are mostly this infrared radiations. You see, if you want to build a night vision binocular, it actually uses infrared to detect people and things. And the light bulb, the visible light, is in that very small region. So when I put this light on, the light produced by this bulb is in this region. And you can see this light is made up of about 4,000 different colors. And as the wavelength decreases, you get ultraviolet. Now, when the wavelength is very small, the energy is very high. Ultraviolet radiations can actually penetrate your skin, and that's why you should not go and sit in the sun for a long time. Ultraviolet radiations can give you skin cancer. Is that right? Okay, let's move on and talk about radiations. Objects emit a wide spectrum of radiation at all temperatures, but a certain wavelength region will be prominent at a particular temperature. Now, you see, I told you that a human body will radiate infrared. Well, a human body will radiate also radio waves and other waves. But at a given temperature, one wavelength will be most prominent, although others will also be present. So, the most prominent radiation emitted by an object depends on its temperature. Now, what is the sun's temperature? What is the surface temperature of the sun? It's about 5,000 degrees Celsius. If you heat this object to about 5,000 degrees Celsius, it will emit visible light. In fact, the most prominent radiation emitted at that temperature. Now look at this filament one more time. This filament is emitting now white light. What is the temperature of that filament? The most prominent radiation emitted by this filament is now white light. The temperature of the filament is in the region of 4,000 to 5,000 degrees Celsius. Now, I want you to watch this filament when the light goes off. As the filament cools down, the prominent radiation becomes red. You watch that carefully. The filament, look, did you see that? Well, it only lasts for a short while. When the bulb goes off, the filament turns red. That means as the temperature decreases, the most prominent radiation at that temperature is red, which has got a lower wavelength. Now, this picture illustrates that phenomenon. Now, as you increase the temperature, the bump on the graph represents the most prominent radiation. See, look at that. At 6,000 Kelvin, the most prominent radiation is the visible light. And the visible light is represented by these different colors. The most prominent radiation at about 4,000 Kelvin and about, yes, is about, that is the infrared, the heat radiations. So if I heat this object to about 2,000 or 3,000 degrees Celsius, it will turn red. It will emit infrared radiation. So the most prominent radiation emitted by an object depends on its temperature. All right. Okay. As the temperature increases, the wavelength of the most prominent radiation will decrease. You can see this is a plot of wavelength on the x-axis and the power of radiation in the y-axis. Now, as the temperature increases, you can see the most prominent radiation shift to the left. Is that right? Shift to the lower wavelength. As the temperature increases, the most prominent radiation will become shorter and shorter. Iron, for example, will glow red about 700 degrees Celsius. The most prominent wavelength at this temperature is infrared, which are heat rays. Well, in other words, the wavelength of the maximum intensity, you can see the y-axis is the intensity. Now, what is the wavelength that has the maximum intensity at a particular temperature? The wavelength of maximum intensity will shift to the left, will decrease as the temperature increases. Is that right? Now, this is a very important law in radiation. What is that law again? As the temperature increases, the wavelength of the maximum intensity radiation will decrease. It will become, the maximum intensity radiation will become shorter and shorter and shorter wavelength. A relation between wavelength of maximum intensity and the temperature of the radiating object is given by Wien's displacement law, a very important law, and I'm going to give that to you. This is what Wien's displacement law says. Lambda max, what does lambda max stands for? Wavelength of the maximum intensity radiation at a given temperature is 2.898 millimeter Kelvin divided by the temperature in Kelvin. The uppercase T means the temperature in Kelvin. This is Wien's displacement law. All